Good afternoon. I'd like to thank everybody for coming to the colloquium today. Today's speaker is Professor Monica Nevins from University of Ottawa. Professor Nevins is well, I wouldn't say originally from Quebec, but she has some strong ties with Quebec. She went to high school in Quebec after eventually going to University of Ottawa and having her PhD from MIT. Professor Nevins is a fellow of the Canadian Mathematical Society and a specialist in representation theory. Has today's talk on why p-adic numbers are better than the real representation theory.
Thank you very much for the introduction. Thank you very much to Alina for having invited me to participate in this colloquium. Oui, je suis née à Val d'Or. Alors, qui sait, c'est où Val d'Or? Alors, je suis plus québécois que la majorité, hein? All right. So I want to tell you and I don't mean to offend with the title, but I am making a slightly controversial point that I think p-adic numbers are a bit better. Okay, then. University of Ottawa colors. There's nothing I can do. Okay. All right. All right. Oops, I'm just going to have to get this working. Okay, hopefully it will work now. So just a quick outline of my talk. So we'll certainly start with what are numbers, especially p-adic ones. Then I'm going to tell you a little bit about representation theory. And then at that point, we'll pause and we'll regroup. And then that's when we go up the steep end. And we really talk about what we want to do. And the last part is a result that I wanted to share with you about representations of SL2QP. But all that comes a little bit later. And my clicker won't work. So, and I don't know why it wouldn't, because it was working just a moment ago. Okay, so, and it's on, and I'm just doomed. It was working before. I just like, now no. Okay, that's it. I guess I can stand right here. Yeah, all right. We'll do it one more second of this kind of stuff. No, you're giving up on the clicker. All right. Make it work.
It's a mouse. It's cheap.
I can use a down arrow. I'm good. I'm cursed. I have one just like that at home, and it acts the same way.
We should throw it away.
All right. Well, it might be allergic to p-adic numbers, but you aren't, so we can make it through.
It's okay. It should go in the trash.
All right. So let's talk about numbers. We got to talk about prime numbers because, to quote George Orwell, all numbers are equal, but some numbers are more equal than others. So a prime number is a number that's not trivial in is not factorizable in a non-trivial way. And so 7 and 13 are prime, but 91 is not because. Thank you. 7 times 13 is 91. So wait a minute. Whoa, it's not so easy to tell if a number is prime. So prime numbers are indeed mysterious. So there's no formula to generate prime numbers or all prime numbers. We're comfortable with that. But then just to, this is a number theoretic audience. Maybe I don't need to pitch prime numbers to you, but I will anyway. We've got that Riemann hypothesis that has an actual correct statement, but you could take it as if the Riemann hypothesis were false, the distribution of prime numbers would be really weird. And boy, would that be crazy. So it's saying that they're random, but they're random in just the perfect way. And the Riemann hypothesis is telling us that should be true. What does random in the perfect way mean? The prime number theorem, again, I've written technically what it is, but the takeaway is if I generate a random k-bit binary number, the odds that it's prime is like 1 over k-ish. So, and then you say, well, that's not very good odds. If I wanted to make a prime number, I've got very low odds of getting a prime, but no. Prime numbers are absolutely jumping up and screaming to be identified. And there's way too many examples. I just give you one. Fermat's test, which is take any number, take it to the power n-1, and take the remainder mod. If you got 1, probably that was a prime. And you do it a few times, and afterwards, my goodness, how could this not be a prime? So we know how to get prime numbers. They are fantastic. We just don't get what they're really all about. All right, so if we don't understand how to understand prime numbers, one way to think of it is, what would the ancient Greeks have done? And I claim that if the ancient Greeks had been as excited about prime numbers and factoring as they were about geometry, they would have come up with the p-adic numbers. So I asked an AI to generate Kurt Hensel, who invented the p-adic numbers, as an ancient Greek mathematician, as one should these days. So what would they have said? They would have said, let's make this geometric. I'm going to say that two integers are close if their difference is divisible, like really divisible by p. That makes them close. And if the difference is not divisible by p, then they're kind of farther apart. So we're taking p equals 3, which will be my p throughout today. 9 is really close to 0 because that difference is divisible by 3 squared. But 9 is very far from 1 because that's not even divisible. So let's have a bit of fun. Let's figure out what this geometry on the integers looks like. So we draw 0, and then I've got to put 1 far away because that's not divisible. The difference is not divisible by 3. And 2 also has to go far away because all these 3 numbers are equidistant from one another. Their differences are not divisible by 3. But when I put 3 on the picture, I've got to put it closer to 0 because that difference is divisible by 3. But 3 is pretty far from 1 and 2. And similarly, 4 is close to 1, but it's further away from everything else on this page. And 5, the difference is 3. 6 has to go back up there because 6 is divisible by 3 from 0 and from 3. So all those things in that top triangle are a distance divisible by 3 from each other, but it's very far from 1. And so now as I increase these numbers, I invite you to think about how I'm getting these. So what I'm doing at every moment, I'm now talking about differences that are like 9 and 18. I'm now getting into 18. It's divisible by 3 squared. So 18 shows up as close to 0 and not that close to 6 because that difference is only 12, divisible by 3, but not by 3 squared. And I can continue on. 19, 20, 21 is close to 3 because the difference is 18. 22 is close to 4. And I'm going to stop there. So if you're looking at this picture, you're thinking about, I've just placed some numbers so that they're relatively close to things there. The difference is factorizable by 3 or by 3 squared. And there's a few other patterns you might see. You might say the biggest numbers, just to avoid that last layer of numbers, take all the biggest numbers and multiply them by 3, and you'll get the upper triangle. And, actually then take the upper triangle and multiply just the biggest numbers by 3, and you get the upper triangle. That's kind of a neat pattern. Would somebody like to share? What shape do they see when they look at these numbers? Anything they want to name? Okay, now this is the class. Come on. Yes, everybody says it. Perfect. This is like a Sierpinski gasket, which you can write with a slight factor to really emphasize that they're further apart, but traditionally is written as if it's connected. Right? For us, these things are really further apart, and we think that each of those triangles is a discrete distance from every other triangle in this entire infinite gasket. I forgot to say, if you have any questions, the right time to ask is when it occurs to you, so please interrupt. Okay, so in fact, we have a fractal structure, and that's that self-similarity that we were just appreciating when we multiplied by 3. Let's make this whole thing more precise. So I'm going to fix a prime p, 3, and then I want to write a positive integer in base p. So you can always do that. So 48, for example, can be uniquely written as powers of 3 with coefficients, as sums of powers of 3 with coefficients in 0, 1, and 2. And it's a little bit easier to write if I just write p for 3. And you can really see that I'm writing as a polynomial, basically, in the prime p. And now the valuation of my number, that'll be the lowest power of the prime that occurs with a non-zero coefficient in this expansion. And it's really just code for saying that's the highest power of p that divides my number. And so in this case, my valuation is 1. That's the red number. Then the size of my number, I'm going to declare that the size of my number, the absolute value, the p-adic absolute value, the Greek absolute value of my number is p to the negative of the valuation. So 48 has size 1/3. And this has the effect that the more divisible it is by p, the smaller the size of the number. So this is how I'm articulating this idea that we have numbers being close if they're divisible by p. Because then the distance between two numbers is you take their difference and then you figure out how divisible it is by p. That's the valuation, and that will in turn give you what the size of the number is. Let's do an example with this. How close were Kurt Hensel and Archimedes? So Kurt Hensel was writing his stuff around 1899 is when he was really publishing the big stuff on p-adic numbers. Archimedes was born in 287 BC. If you do that difference, including that zero, that problem they had with not knowing the year zero was in there. But if you do it properly, the number of years between those two in p-adic norm is the norm of 2,187, which is about 0.00005. Coincidence? Okay. So we have a notion of distance that makes sense, and we're going to call that our absolute value. Now, my next step is, oh, wait a minute, I was just talking about the positive integers, but I want rational numbers. Those are definitely interesting. And my first claim is that every rational number could be written in this form. This is slightly more general than the form we had before. When I said base p, that was just a finite polynomial in p. And now, if we're looking at this, we agree that we're allowing our sums to start at maybe even a negative power of p, so that I could have 1/9 in here. And I'm going to allow myself to go off to infinity. And well, all right, now I claim that every rational number shows up in this form, even negative numbers. And to argue this, I'm going to show you that -1 is equal to this geometric series. Now you look at that and you say, it's not equal. That stuff is like higher and higher powers of p. That's going off to infinity. And I say, no, 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 no. Those powers of p are getting smaller and smaller and smaller. So this converges, no problem. And then you might say, well, you know, and many of you are extremely clever, and you're sitting there doing the geometric series, and you say, oh, okay, fine, that's -1. Let me give a more elementary proof that this is -1. I'm going to add 1 and get 0, okay? So we add 1. P minus 1 plus 1 is p, but that shouldn't go in the units position. That has to go in the p's position. So I have 0 and I carry the p. Then you have p plus p minus 1. You get p squared, which means 0 plus you carry the p squared. And then you keep carrying, and you're carrying a smaller and smaller number in my sense. So this thing is converging to 0. Therefore, it was -1. Similarly, if I want all the rational numbers, what I can do is I can just do long division. So I have 5/12 here. I write out their base p expansions, and then I do long division in the usual sense, but with my higher powers to the right, like we do polynomial long division. And you'll always get a beautiful series that starts somewhere and then continues on to higher powers to the right. And in this case, it's this beautiful kind of repeating 0,2,0,2 kind of expansion. All right, let me say, well, that's really nice. So all my rational numbers have this expression. Now that I've accepted that p of the n is 1 to 0, all my numbers have this expression as some kind of series. Well, now I want to tell you what p-adic numbers are. And this is where we say things like, even Pythagoras knew that the rational numbers were not enough. They knew that the square root of 2 was not going to be a rational number. So we know there should be more. And so my definition of the p-adic numbers is now every series that appears in this form, the coefficients from 0 to p minus 1, higher powers of p, potentially an infinite series. And I just want to contrast that with our definition of the real numbers. So if you look at the real numbers, you'll say, well, you know, it's the same thing. It's powers 10 to the -1. So that's so that I can have the expansion occurring in the same direction. That's not how we usually do powers of 10, but this is nice. It's a very similar looking construction for how we defined all the real numbers. But, you know, notice with the real numbers, you have to awkwardly put this little plus or minus at the front because you can't get -1 as a sum of powers of 10. And then, you know, I put this little squiggle here because you all know that, well, 0.9999999 is actually equal to 1. Now, I don't have these problems with my p-adic numbers, all right? So, okay. So my claim is that QP is definitely bigger than Q, definitely has more than just the rational numbers. Maybe I could have said in the, in the real numbers, you know that the rational numbers show up as the ones that have repeating coefficients. That's exactly what happens with the p-adic numbers. The rational numbers have repeating expansions. So it's the same kind of thing. We have a lot more numbers in QP than we do in Q, but we have the added advantage that somehow QP retains more knowledge of that prime p than did the rational numbers alone. So an example of this, without giving you the statement of the theorem, is you could think about solving x squared plus 1 is equal to 0. If you wanted to do this over the rational numbers, you'd say, no, there's no solution. That's fine. Over mod p, if I just work mod p, I say, well, 2 squared plus 1 is 5, and that's 0 mod 5. So I can solve this mod 5. Hensel's lemma then says, perfect. Then you can solve it in Q5. There exists an infinite series that has that same initial term that will solve that solution. It will solve x squared. So it'll be a square root of -1. So I is an element of Q5. And similarly, because I can solve x squared is equal to 2 mod 7, thank you, 3 squared is equal to 2 mod 7, then I have a square root of 2 in Q7. Now, but I is not in Q7 and the square root of 2 is not in Q5. All right, so it's not like I get all possible roots in all p-adic fields. Morally speaking, what is a good way to think about it is that the rational numbers are exactly the only numbers that are in common for the real numbers and all the p-adic fields at once. They're the common core of all these things. And that kind of shows a little bit of why these are interesting to us. Because when we're thinking about solving things over the rational numbers, we would use techniques from real analysis because like it's really easy to do stuff over the real numbers, but we're only seeing like a little aspect of those rational numbers. And we see much more if we take them all. And because I'm in an yes question.
Why are you intersecting with R?
Because I want to say that it's all the different completions of Q. So R was a very natural completion of the real numbers, but I accept and I would like to say that all those other completions are as well. And now if the statement is it true that you have to have R in this statement? That's for the number theorists in this audience. But I would, I'll blame it for the, thank you. All right, and yeah, okay, for the number theorists, I've written it as an intersection, but these sets do not live in one universal set, so you're not allowed to do an intersection at all. Okay, I bet to make it better. All right, what we're missing about the rational numbers by living in the real world is this local global principle. And this is an idea, not a theorem. It's an idea that if you're going to be able to solve an equation, it's going to be solved over Q, if and only if you can solve it over the real numbers and all the p-adic numbers. There's something about this plethora of ways you can solve it, and in the intersection, you get Q. This has a couple of theorems that are absolutely true, and the most famous one would be the Hasse-Minkowski theorem. So Minkowski there on the left, he was 18 years old, and it was this puzzle at the Academy or something like that. And so he submitted his solution that did this magnificent thing. And then after the invention of the p-adic numbers, Hasse came along, and then he really proved it. So, and the statement goes something like, so you're trying to solve an equation like a sum of squares is equal to 0 with coefficients in the rational numbers. And you are wondering if you can find a solution with all the xi's rational. That's a great problem. That's like what algebra was for 2,000 years, was solving things like this. Well, the answer is you're going to get a solution if and only if you can solve it in QP and in R, and QP for all P and in R. And why that's exciting is it's dead easy to know if you have a solution over R. That's what calculus is for. And over the p-adic numbers, you just need to solve it mod P, and then you use Hensel's lemma and you're fine. Approximately, sorry, the star for the number theorists in the audience there. Okay. So we really appreciate this local global principle. It's telling us that something with the p-adic numbers is telling us more rational numbers. Now, we got to talk about representation theory. So representation theory is about understanding algebraic structures. So let's start with understanding the algebraic structures of the p-adic numbers. So here they are again, my p-adic numbers. And in particular, this is a group under addition. So this is where we up the ante. I now assume everybody knows what a group is. All right. So we go and we say, what are some subgroups of our group? Like that's how we understand a group. And I say, ooh, one of the obvious ones, ZP. That's when you take all the power series, things that start at 0 or after 0, all of those without p to the minus. And you could say, oh yeah, those are all the elements of norm, of absolute value less than or equal to 1. Well, it's also all the numbers of norm less than 3. because the size of something is always a power of my prime. So I can have size 1, 1/3, 3, 9. I don't have anything of size 2. So the things of size less than 3 is the same things of size less than or equal to 1. And then, okay, so and this ZP, that was that Sierpinski gasket that I had drawn earlier. And what we should imagine is the p-adic numbers is if you continue that Sierpinski gasket off to infinity off the bottom of the page, okay? That's what we multiply by 1/3, 1/9, and so forth. Inside ZP, I could take PZP, all the numbers that are at least divisible by P. And that's the green triangle on this page. And you could say, well, that's all the elements that have norm less than 1 or less than or equal to 1/3. And P squared, that's the very top triangle of the 3 green triangles. That's a subgroup, and it's all the elements of size less than P or less than, elements of size, sorry about that, less than 1/P, which means less than or equal to 1/P squared. Sorry about that. So when we're thinking about this, I've described these sets in 3 different ways. They are subgroups, they are open balls, and they are closed balls in the topology. So I have the open balls, which are triangles for me, are also closed and bounded balls. So I have a ton of compact open subgroups. That's a really interesting structure on p-adic numbers. Okay. So now we want to understand this group, we should use representation theory. What is representation theory? Representation theory understands groups by how they act on complex vector spaces. Again, an asterisk for all those people who are experts at everything that is excluded from that definition. This is all we're going to do. So I'm thinking of my group and I want to on a complex vector space. So my group of addition, p-adic numbers under addition is abelian. So I know that I only need to worry about one-dimensional representations. And then we say, well, what do I mean by acting? Well, I should act linearly on a one-dimensional complex space. And that means I should act by multiplication by a non-zero complex number. So what I'm looking for are maps from my p-adic numbers with addition to the multiplicative group of the complex numbers, satisfying that they preserve all the structure I've got, the topology and the group structure. So I want it to be a continuous map, and I want it to be a homomorphism, and I'm using additive on the right and multiplicative, or additive on the left and multiplicative on the right. Okay, so now hang in, now we're going to do a big proof, and it's got a lot of steps, but you can do it, all right? So I want to classify all of these. I don't want to classify. I want to tell you something really amazing about all of these maps. One-dimensional representations of QP under addition. So it's a map from QP, this infinite Sierpinski gasket, to the complex plane or real two space as you wish. All right. So in fact, I'm just going to localize. I'm just going to look at the ZP part of it. Okay. So it's a homomorphism. Therefore, 0 goes to what? It's continuous, which means the inverse image of an open set is open. So I'm going to take an open set around 1. And then when you take the inverse image, you're going to get an open set around 0. And I've drawn it as, so it's the Sierpinski gasket intersection with this open set. Look inside that set. For sure, you can find a compact open subgroup sitting inside of this set, which I've put in red. Some power p-adic. In this case, I could take the bigger one even, but I just chose that one for illustration. So that is a subgroup sitting inside of this inverse image. I have a homomorphism. The image under a homomorphism of a subgroup is the subgroup. Okay, so now quick, what subgroups can I have inside that little bubble I drew around 1 in the complex numbers? Subgroup is closed under powers. If you take anything of norm bigger than 1, you're going to leave that set U. Anything norm less than 1, you're going to leave that set U. Anything on the circle, you're going to go around the circle. In fact, you've only got one subgroup. So that entire open set has to go to the number 1. Now, wait a minute, and what does that mean? I have a homomorphism. That means every triangle of that size all go to just one number. Why this is magnificent is we were getting a little bit scared about this fractal nature of my p-adic numbers, like, oh, it's going to be really hard to understand the maps. But it turns out we immediately simplify everything. These functions are all going to be locally constant. You're always going to be able to find some triangle on which it's just the constant function. Okay. So with that in mind, I think we're ready to compare. So let's talk about p-adic numbers versus real numbers. So in p-adic numbers, the best functions are locally constant functions. That means they're constant on open neighborhoods, on open sets, and they are completely indistinguishable once you restrict to a small enough neighborhood of 0. In real numbers, I say the best functions are analytic. And analytic functions are totally determined by a small enough neighborhood of 0. And now you think, so this is really polar opposites, right? Now, what does that make p-adic numbers better? Well, what are some of the things we like to do with numbers and functions? Well, we like to integrate them. Integration in p-adic numbers is about some discrete sums. I just have to add together the values that it takes in all these open sets. And that's my integral problem. Integration on the real numbers, we have 3 calculus courses for that. So just saying. All right. Okay, so now that's great. We have p-adic numbers. We agree they're kind of cool. They're very nice. What is our goal with all this? So just one page, and oh, I beg forgiveness for all the number theorists in the audience. Okay, you can take me to task afterwards, all right? So the big question in number theory, how do we understand the Galois group of Q? And maybe I'll say the Galois group in a nutshell is the thing that answers every question about all the solutions of polynomial equations over the rational numbers. Like the things that we're doing 2,000 years of algebra are going into this beautiful Galois group. It is a group though, so how do we understand it? With representations. Now, that part would be fine, and we would be still stuck here if it weren't for Robert Langlands, who the thing was, the story is that he had to substitute for a colleague and teach a class in local class field theory. And he's saying, oh, it's a real shame there's no non-abelian local class field theory. And then through a sequence of letters and conjectures and stuff, he laid out a program that's more or less employed at least half the people in this room for many, many years. And it's a sequence of conjectures that's saying something about how we could understand the Galois group of Q if we could just really understand these representations of these groups over something very closely related to rational numbers and p-adic numbers and all that stuff. And then the local global principle applied to this whole philosophy says that actually it's a pretty good place to start is just to try to solve this over the real numbers and over all the p-adic numbers. And if you could do that, you'll have some mileage towards the big unsolvable, probably solvable problem. All right. And in a very brief nutshell, this local Langlands correspondence is saying it's a conjectural bijection that is known for all the cases that I'll talk about today, SL2. And for each connected reductive group, though, it's saying that you could take, on the right-hand side, you could take representations of the Galois group, kind of, something like the Galois group, and you could take special representations, for example, projective representation of extra structure. And if you just figured out what those classes of things were, then on the other side, there would be this bijection with something that's much easier to understand. And that is we take these matrix groups and we understand their usual complex representations. So it's setting up that we can solve these incredible problems in number theory by doing some representation theory on kind of friendlier groups, if I'm allowed to say so, matrix groups over fields. All right. And then the promise is that conjecturally we put it all together and we're going to have the answer to the world's mysteries about Gal Q. Okay, all right, sorry, very scared about doing that one. All right, here we go. Let's get into friendly turf. Let's say that we're going to do representations. I'm going to take G to be SL2. All right, SL2, that's the set of all matrices that have entries in QP, the p-adic fields, and the determinant is 1. And this is a simple algebraic group. Completely lovely. And being simple means that if you try the argument we just did about what a finite dimensional representation would be like, you can actually come up with, oh, well, it would have to have a big open subgroup in the kernel. And it doesn't have any big open subgroups. So you can only have trivial representations if they're going to be small. Okay, so that means we want infinite dimensional representations. Now, I can't just have any infinite dimensional representations. I need to get this notion of this continuity in things. And what we get from that is smooth. So my word for smooth is not infinitely differentiable, although really I would like to replace infinitely differentiable. And it's this idea that I will say that my representation, remember, it's acting on a space. Now, the space is infinite dimensional, but you could take any one vector in it, and you could say that the way the group acts on it, there's an entire compact open subgroup that just fixes it. So that's very analogous to the spirit of what we were talking about before. So a smooth representation is one. So for every vector in the space, you can find a compact open subgroup that fixes that vector. I warn you, a different compact open subgroup for every vector, okay? So I say compact open subgroups as if we're agreed that they exist. Let's get a feeling for these. So in QP, we had a lot of compact open subgroups. That was those powers of ZP or PZP. So here's a perfect example of a compact open subgroup of SL2. Take all the matrices where every entry in the matrix has norm less than or equal to 1 and is determinant 1. And then its inverse will be there, its products will all be there. That's a beautiful compact open subgroup. And once you realize that that guy is a compact open subgroup, you can see smaller subgroups in there. You could take all the matrices that are congruent to 1 mod p, or all the matrices that are congruent to 1 mod p squared. And those will give you, again, subgroups. Again, I mean matrices with determinant 1. Now, what have I done here? I've filtered this maximal compact by some smaller ones, and there's an index 0, 1, 2. That 0, 1, 2 is reflecting the valuation kind of, right? So the bigger the number, the smaller the subgroup, just like with PZP, I was getting smaller the higher the power of P. That first index, ooh, that's an interesting index. That index comes from the Brouhat-Heath building of SL2, which deserves a talk unto itself. But maybe what you can be thinking of is that my element X that I started with, maybe that was this point of the Brouhat-Heath building, right in the center. And it's like a choice of basis with respect to which I represented my matrices. Now, the Brouhat-Heath building has an action by the group that kind of does a whole lot of symmetries on this thing. And sweeping a little bit under the rug, and I'm sorry for it, but you can conjugate that group. If I conjugate a group by, if I conjugate my GX0 by any invertible matrix, I will get another compact open, maximal compact open subgroup. So there are infinitely many different maximal compact open subgroups, and they are indexed by all the vertices in this building in a very, very nice way. And so a point X in the building is corresponding to a compact open subgroup that has a lovely filtration because you can just conjugate the whole. Okay. And there's lots to be said about the building, but let's just go with that. So my X will always be a point in this building. And maybe to visualize this, so you think like that compact open subgroup that I have there, that's like the perfect one, right? Like, yeah, that's the one. And so that's like a round sphere. And then if you think about all the other ones, maybe they're like ellipsoids. Because you could imagine being like neighborhoods of the identity in like a lot of different ways. So we got the perfect one maybe, and then we have a whole bunch of other ones. Okay, good. All right, now I got to talk about the depth of a representation. So I said that as a representation was smooth, meant that every single vector, there was a compact open subgroup that fixed it. But it's like a natural question you start to have is like, what's the biggest compact open subgroup that fixes any in this representation? So I know that everything is fixed by some, but maybe a lot of vectors are fixed by tiny subgroups, and then there's a few that are fixed by a really big subgroup. So I can come up with a definition from that, and that is, since I now have a uniform way of talking about how big one of these subgroups is by that filtration I was using, I can say the depth of a representation is the minimum value of R such that there is some point on the build and some vector, non-zero vector by representation that, okay, so that open subgroup fixes that vector. Now, actually, you see a little plus there. It's because it's actually nice is to keep track of the very last subgroup that doesn't fix anything. And then right after that, you get smaller than that and suddenly stuff. So that's what R and R plus are about. So R plus is saying like R was the last place where you didn't have fixed vectors. Is that clear as mud? So maybe just to bring in something, just reaching out on what people might be interested So if you have a depth zero representation, so then that would imply that you have these vectors that are fixed under gx0 plus, a fairly big group in there. If you take all the vectors that are fixed under gx0 plus, it's actually a nice finite dimensional subspace. And it will carry a representation of this quotient group that I've written there. Now, I'm not sure that you can really see from what I've written. It really is SL2 over the finite field. It's a nice finite group of Lie type. And it's over Z mod PZ. And we knew the p-adic numbers were going to be remembering something about Z mod PZ. So it turns out that inside this infinite dimensional representation, I have this little tiny finite dimensional piece that carries a representation of this finite group of Lie type. And we know everything about representations of finite groups of Lie type. They have so much arithmetic information, it's insane. Cool is that very often this little piece dictates the entire rest of the representation. So there's an awful lot of the arithmetic information of our representations sitting on this first piece. So are representations of my SL2 trivial near one? Well, the first thing I say is no. There's no one compact open subgroup that fixes every single vector in the whole representation. That does not happen. I really have interesting infinite dimensional representations. Now, and why is this? So now we got to get into the question of why am I not getting trivial near one with such a trivial condition? And the way that I would say this is that when we're doing representation theory, it's not so much the elements that matter, but it's conjugacy classes that really matter. So if you're thinking about representations of finite, it's characters and things like that. So our question is, or really I'll say, in QP, which was an abelian group, all the conjugacy classes were just points. So if I was saying, take all the open neighborhoods of 0, and what do you meet? Well, the only thing that's in all those neighborhoods is 0. You can avoid every other conjugacy class. What conjugacy classes will meet every neighborhood of 1 of the identity in SL2 QP? Those are the ones that I can't avoid, and they're somehow contributing to the non-triviality of my representation near 1. Here, so I'm just going to up the ante quite a bit. I'm going to say, handing fact. SL2 is an algebraic group and it has a Lie algebra, which is linear. Everything linear is divine. So we much prefer SL2. And what's even cooler is there's an exponential map that goes from a Lie algebra to a Lie group. Exponential maps are defined by series. Yay. Oops, they don't converge on all of QP. Ooh, but they do converge on a neighborhood of 0. So you are allowed, and it's a G equivariant map. End of story says, if I want to understand what's happening in a neighborhood of 1 in my group, I might as well look at a neighborhood of 0 in the Lie algebra, and I can translate back and forth with exponential. And here, ooh, I'm going to do something over the reals, just because it's really hard to draw anything over the p-adics. So just for going back in the real world, you want to think about what happens when I conjugate matrices in the Lie algebra of SL2. So the Lie algebra of SL2 is all those matrices of trace 0 instead of determinant 1. You take all those guys and you do conjugation. And in the coordinates that I've given here, this is an excellent exercise. You can actually work out that the conjugacy classes are hyperboloids. Specifically, here's a picture. The picture might be hard to see, but you have all these hyperboloids of one sheet. Those correspond to matrices with real eigenvalues. You have some hyperboloids with 2 sheets, and those are 2 parts. These are 2 orbits, distinct orbits corresponding to imaginary eigenvalues. And on the boundary between them, you've got this double cone. Now, what of these will intersect every neighborhood of 0? That double cone. And that double cone is exactly the orbit of your nilpotent elements. In fact, under SL2, you conjugate by matrices of determinant 1, you'll get 3 nilpotent orbits. So you've got the 0 orbit, then you've got the upper cone, which is everything that is conjugate in SL2 to 0, 1, 0, 0, and then you've got the lower cone as well. All right. And the point is that every neighborhood of 0 has to meet every one of these nilpotent orbits. But you can avoid any hyperboloid you want just by getting a little bit smaller. Okay, so back to p-adics. Over QP, there are 5 nilpotent orbits because QP is much more interesting than R. And it's because if you think about, oh, why did it be minus 1 doesn't have a square root in the real numbers. Okay, so p-adic, what doesn't have a square root? P doesn't have a square root in the p-adics. And also this Hensel's lemma game, you can always find a number like -1 or 2 that doesn't have a square root. I called it epsilon. So you end up having 5 distinct nilpotent orbits. Caveat, p is not equal to 2, and this epsilon has valuation. Okay. So it turns out that what we should really think about is all those nilpotent orbits and how they're really messing up as we try to restrict to a. And this has been known for a long time. Harishchandra and Howe came up with these are pioneers in the field of representation theory of real and p-adic groups. And what they said, okay, first take the character of your representation. The character of a representation, say, of a finite group is you just take the trace of each matrix of pi of g. I've got infinite dimensional representations, and you're quite possibly a little bit annoyed at taking the trace of an infinite matrix, but I'm telling you, it kind of works out if you just broaden your minds, accept generalized functions, distributions, partially defined functions. Like it just works out great, and the function is even integrable, so it's really lovely. Okay, so we have a beautiful function that's like the character representation, and just like representations of finite groups, this character, if I have 2 representations, and if they have different characters in there, then they're different representations. They're not isomorphic. So it's really strong as a property, even if it looks like it's not very much. And Harishchandra and Howe proved the local character expansion in the 1970s. It was quite general for connected reductive for over and Lie algebra's little sheet. So they said, hey, look at this. Every nilpotent orbit, that actually gives you a function from the Lie algebra to the complex numbers. We can write it down, Fourier transform of an orbital integral. And then you could take the character representation. And what turns out is, even though the character, there's like, infinitely many representations, but there's always a small enough neighborhood of the identity of 0, so that if I take my character at the exponential of that small neighborhood, I can write it as a linear combination of just those 5 functions that we have there. This is insane. You have infinitely many representations, but it comes down to like these functions in a neighborhood that really are, well, not trivial, but they're just linear combinations of 5 things. Like there's hardly any degrees of freedom left. So this is massive, and this is really beautiful, and it's almost like what you can do. And it's kind of saying the triviality, but it's not in terms of representation theory. Like I had to take the character of my representation. I'm doing an exponential math. I've got Fourier transforms in here. There's questions about normalizations for me and talk about what these coefficients are like. It's a very nice statement in harmonic analysis, and I want a statement in representation theory. All right, so that's what we're on the way to do. So in order to do this, I should tell you how to construct representations from nilpotent orbits. That's our goal. So easy case, 0 orbit, trivial representation, done. All right. Now let's think about those other 4 orbits. All right, so you're taking one of these orbits, and I should say, I'm going to construct a representation of a compact open subgroup, a GX0. That's my goal at this game. So I fix a vertex in my building, and I take one of my nilpotent orbits. Then the first thing I'm going to do, so I can write orbit as the orbit of a certain element, I am going to decompose that orbit into its disjoint union of orbits under this compact open subgroup. That's way better. Each of these things is now compact. That's really lovely to work with. So we have a horrible kind of orbit we've written as a disjoint union of orbits under this compact open subgroup. And if you're looking very carefully at the tiny font, you'll see actually I jumped by squares, and that's a neat artifact of what's going on here. Okay, so I've written my orbit, my nilpotent orbit, as a disjoint union of orbits under my compact open subgroup. And then we know how to construct an irreducible representation of GX0, my maximal compact, from just the geometry of that little bit of nilpotent orbit. Or you could think as coming from the linear algebra that produces this nilpotent orbit. And this has been known since Shalaika, who in his thesis wrote down all irreducible representations of this kind of group GX0. So there's a way of producing a representation of this tiny compact open subgroup that's finite dimensional and irreducible from each one of these little orbits that we have. So what we're going to do, we just add them all together, an infinite direct sum. Now I've got this infinite dimensional representation of compact open subgroup, very reducible. And this is really just using the geometry of the orbit to produce it. No, it's independent of all the choices it might play here. Okay, and it's a representation of gx0, so everything that depends on this in the subscripts. Okay. And the result of this is the main term, which is saying that representations of SL2QP really are kind of trivial near one. And so this theorem is, so suppose that P is not equal to 2, because 2 is a really odd prime. So now take any irreducible representation of SL2QP. It has some depth R, is interesting. And then what we say is, there is a set of non-zero nilpotent orbits called the wavefront set associated to that representation pi, such that for every G in that neighborhood, GXR plus, remember that's just when you start to get fixed points. So inside that neighborhood, your entire representation looks just like, add a couple of those infinite dimensional representations associated to the nilpotent orbit, just remind the trivial representation, and that's all it looks like. The representations themselves are kind of trivial near the identity. They're just combinations of these orbits, representations that the nilpotent orbits forcing on us. So this is super cool. And why build with it? Well, one, this is a purely representation theoretic interpretation of the local character expansion. And it's a lot simpler than the local character expansion. This one doesn't have some of the hang-ups of being over fields of characteristic P as the other one does. And it's very satisfying in the sense that look at those coefficients. Like it's like just add together some representations. We know that with some normalizations, the local character expansion, the leading coefficient should have integer coefficients, positive integer coefficients. And here we're discovering why. It's because we're actually getting in the Grothendieck group a linear combination of these kinds of nice representations. This thing I call the wavefront set, and some of you might know the wavefront set has another definition in the analysis world, and that's all coming from the local character expansion. It really is the wavefront set of the character. And the way we get it, though, is we don't have to go to the character to figure out the wavefront set. We look at how you built the representation, and the geometry of that is actually dictating how to get an element that will pick out those nilpotent orbits. So we're pretty happy with how much information we're getting out of this kind of thing. So maybe I'm near the end here. My final sally on representation theory is better than we know would be, okay, so what about the real case? Now, the real case I will give you has been studied for a lot longer than the p-adic case, and it has some pretty impressive theorems, okay? And we do have a local character expansion over the real numbers. So if I have a Lie group of real numbers, I can write down this, but I cannot possibly write this in the same way as we have in the p-adic case. I do not have some small open subgroups on which I can write down an equality of representations. That's hopeless. I don't have any of those. Now, our goal is to construct the wavefront set from the representation without having to go down to the character. And this is using algebraic geometry and its associated varieties, for those of you who know. Now, Langland said that what we're supposed to have are these automorphic representations. And those are the ones that are going to tell us about the Galois group of Q. And what we know conjecturally is that any one of these should be able to be written as a product of local factors. So a bunch of representations of the reals and the Q2 and Q3 and all QP. And one of the conjectures out there is that we should be able to see that the wavefront sets of all these guys are all totally different, right? Because they're all sitting in different fields and different things. They're all coming from a common core source. There should be an element defined over the rational numbers. So that means it's also defined in all of these localizations. Such that if you take the asymptotic nilpotent cone on that element, think of if I had any one of those hyperboloids, you could say like asymptotically, which nilpotent orbits does it look like? So if you had the hyperboloid of two sheets, you have the bottom one, the top one, it looks like the two nilpotent orbits. If you had the hyperboloid of one sheet, it looks just like this top nilpotent. That's the asymptotic nilpotent cone. So the idea is there should be an element defined over the rationals. So if you do the asymptotic code at all the local places, you're going to see exactly the wavefront set showing up. Now, what's nice about that is in our p-adic work, I can totally give you the candidate elements, or at least I have a lot of clues about this candidate element, because we can do this over all the primes P. And basically, we kind of know what kind of element we should get, and it's from the construction of. So, and with that, I'll give you some notes for further reading, and thank you very much.
Okay. So you told us about this, and then you've told us about this like very nice expression. If I understand it, it sort of takes place at the subgroup given by the depth. Is that what I should? Yeah,
That's right. So you're thinking about this representation, and it's just a bit where it starts to become trivial. That's when we can say this is how to look at the entire representation.
Can you use that to count how many fixed vectors you have? Like, what's the dimension of the fixed vectors at the first level where you do see fixed vectors?
Okay, can I count the dimension of the space of vectors G are? Yeah. And okay, to the extent that you fully understand these tau OF, yes, absolutely. And one of the pieces of the proof, so I actually know how to put down all representations in all. And it was to figure out how to make these guys out. The plus or minus copies of the trivial representation in the front are actually capturing a little bit of that. Like, so the very first place where I start to be trivial, I'm not going to have as many copies of the trivial representation. And as I go down, that n is going to increase.
Thank you.
It's a question on Zoom. If these you came to the
Well, we're not hearing you. So maybe you'll have to type and somebody will read.
I'm sorry, can you hear me? Jose just left. We had a little Calgary watch party gang here. Thanks for the talk. It was fantastic, absolutely fantastic. I was wondering, I've done a little bit of reading recently on some of the nilpotent orbit stuff in the real case, and I know there the sort of correspondence you get is nilpotent orbits and unitary representations. So I was wondering, like, is there any kind of extra thing you can say here about like unitariness or tempered or something?
That's a really good question, and David Logan has been asking me this a lot, and I still don't have an answer, which is embarrassing because he's my supervisor. Okay? And I don't see as yet, I don't understand how to see temperedness or unitarity or a lot of those other characteristics that people who maybe, like on the language program with irreducible admissible representations, those are the only ones we really talk about. But you know, in the rest of the world, maybe unitary representations or tempered or a lot of those other things would come more into that. But I won't see it in the wavefront set, for example, because I could have a unitary physical series that has the same wavefront set as something that's very non-unitary. So I think I'm losing control over such global properties of a representation when I restrict down to neighborhoods.
Thanks.
Related point, just like, can you just give us any idea of how this wavefront set depends on height, like any sort of qualitative field?
Okay, so I would say that representations of SL2, you have a whole bunch of them that are principal series representations, beautiful long structures, and their wavefront set typically are all four nilpotent orbits, so they're fat and generic. And then you have supercuspidal representations. Those ones are lovely because the matrix coefficients are complexly supported, like that's a supercuspidal representation. And those have much more interesting wavefront sets. And it really is jumping between some of them, the most special of the representations. There's wavefront that is just one of the four orbits. But generic supercuspidal representations will pick up two of them. But they pick up pairs of them in kind of weird random combinations. And what turned out to be the secret behind why they're picking that out is if I want to make a supercuspidal representation, I've got to start with a subgroup called the torus, and specifically a compact torus inside the SL2. Now, if you take an element of the Lie algebra, that compact torus, and you can think of what its hyperboloid would be, that is the element in the structure that's picking out just a couple of those ones. So because the tori are somehow not really uniformly spaced out or spread out in the algebra, and they're the ones that are picking out just one or two of those.
Any other questions?
What about this generalized SLN?
I so want it to be true. Like, I mean, I think this should really work. At a mechanical level, proving this composition took a long time because, okay, little side fact. So you think that a very natural way to get about this is you say, oh, okay, no problem. Take a representation of your p-adic group, restrict it to a maximal compact open subgroup. So then it's a direct sum of irreducible representations of a nice little compact group. So just go ahead and write down what all those pieces are, and then you can restrict what you want. We do not know the classification of the representations of these itty-bitty compact open subgroups. We don't have a theory. There's people who say the problem is wild. This is how terrified they are of this problem. I said too, we got a list to like if we went to us in 1967. Rank 1 groups, I have a student who's working on this and it's looking good, so I think that'll work out. But once we get to higher rank, you can't start. Let's just restrict because we don't know enough representation theory. But I am really hopeful that we could think about it from the other way, the way that I presented here, which is, oh, but I know that nilpotent orbits, maybe we can construct those representations. And it would be enough to tell us our answer.
What is the classification of nilpotent orbits?
Okay, so yeah, so do you know, so represent, so nilpotent orbits is SLN are just going to be about plus or minus. If I want the principal nilpotent orbit of SLN, I'm carrying what nth roots of unity, or so not nth roots of unity, but missing nth roots. So and so if p is not equal to, well, okay, so if p is nice, then you're really just going to get n squared number of nilpotent orbits. So you get a lot more nilpotent orbits than you do in the real case. But it's fine.
Yeah, so you're talking like jazz are better than Beatles.
Yeah.
So if I know all these about the representation of cat, does it still lead to some insight to the representation of the human right? Are there some phenomena that resonate even though that?
I definitely want to say that there are phenomena that are going to resonate. And there's this, because, you know, as always with representation theory, we keep coming up with like it's the same theorem, but the proof is totally different. And some of the ways in which this is coming up, the way that we're getting the wavefront set, that associated variety thing, I don't see any analog on the p-adic side. But the thing that we talked about on the p-adic side has a real analog. And this is in the paper that I cite there by Adams and Hogan, trying to hint at things like that, that maybe we're going to get a simpler insight if we've got this more arithmetic view. That would be, that's dreamy.
You know, this framework, that's mathematics. In my real space, more than mathematic ones. I mean, are you know,
I don't know this kind of the philosophy is that what? I definitely believe that we should be thinking about reals and p-adics together, not discriminating against those poor real numbers. I will include them in the bunch. But yeah, like how about there's a lot of pieces of this where I feel like there's some symmetry that's going on and there's a lot of story that's back. Yeah. So I'm not totally dissing the real.
Any other questions? If not, let's thank the speaker again.